Let's learn about embeddings. Actually, wait, no, hold on. It's not really about learning embeddings. It's really more about if you want to dip your toe in the water for AI. You want to learn all about AI? There's a lot to it. However, there's probably a good place to start. And we have a great article here from Bryant, who's going to walk us through learning about vectors and embeddings and ways that we can actually leverage those things. You don't need to have an AI model or an ML model. You can use these techniques, which are precursors to AI. It's actually a really good way to get started. And we can take a look here. And the whole idea is vector embeddings that we can use in a vector database to search for similarity between items. This is a more natural way to search for things as from a human perspective. We have language, we speak language, we talk about various things, and we have a lot of ideas and other similarities in words and similes and dictionaries and thesaurus. We have a lot of words that we have intention to target for specific. We're looking for something. We're looking for something specific, and we're able to find it if the embedding in a vector search can more closely match with a large database of vectors to find what we're actually looking for, even if we don't use the right keyword. This is the whole idea between Google search and other kinds of search engines, is the ability to better provide the results of what you're actually looking for. And Bryant describes here, says once he started using vector searches with embedding for actually searching for something rather than keywords, it actually becomes that much more better of an experience. And like, why isn't this used everywhere? Well, it's not used everywhere, or it hasn't been yet, but it's probably soon will be, because of the indirection that's required when you're vectorizing a search string into a series of numbers and applying attributes to those numbers. And that's called a vector. It's embedding, essentially, an embedding process. And that is where it's missing. And once you have that, now you can start doing vector searches. So we're getting started with AI by taking a look at embeddings and vector search. And guess what? This is actually a pretty good way to start with it, because of how simple it is, and it doesn't require all those advanced algorithms that you typically have to deal with machine learning models and deep learning. It's actually pretty straightforward. You only have to use a few components together, and you can provide a significantly improved search experience for users by using vector embeddings. The whole idea behind here is that we'll use an embeddings API that works, allows us to create a similarity, measuring similarity between items. So you can throw a string of text into embedding. Out comes an array of floating point numbers. Congratulations, you've just embedded a sentence or a search and created a vector, which is just essentially, it's an array of numbers. An array of numbers can also be called a matrix. So these terms are interchangeable with, it can be arbitrary input. Any kind of input. We're going to be talking about text in this case, though it could be any kind of data, sensor data, video data, right? What we're currently looking at right now on the screen is video data. We can have audio data, like any kind of audio. That works perfectly fine as well. Using pgVector, which is a vector indexing system, it better provides higher performance with a large number of vectors. So say you have a database full of words in a dictionary, and you want to vectorize each of those words. It's quite a few words. And so in order to provide a better performance experience, you can use something like pgVector, which does a specific slicing of the data to better partition and create faster search results, essentially. Even better, you can combine it with other standard SQL logic. So you can have filters and wheres and transforms and do extra math on top of it that gives even better results. And so the great news is, like, unlike any other kind of AI models, LLMs, even large language models, working with embeddings feels a lot like deterministic code, because it's pretty much. Let's take a look at a project that has implemented the vector search algorithms with pgVector, and it leverages embeddings. The idea is we have a set of icons, and this is actually a pretty powerful v0.app is the domain, a set of beautiful icons. And they have categories and associations and a whole bunch of other metadata surrounding these things. Now, the problem is there's so many icons. There's a lot of icons. And if I wanted to search for any one of these, I would normally do it by keyword and tags and things like that. The challenge is I might have a more desired, I'm looking for something specific, and I want to find something that kind of matches my expectations a little more. As a human, I'm not a machine. I won't have the exact word or phrase that I'm looking for, but I'll have something that is approximately nearby of that search. So I can throw that search term in here. So say I want something that looks kind of like a speedometer or a tachometer, or it's sort of like a gauge, right? So let's see if I type in gauge. Okay, so I get a whole bunch of what I'm looking for. These are speedometers and tachometers. So if I type speedometer, will I get something similar? Will it come back with results? And it does. And as you can see, not all of these, probably none of these icons in here necessarily have the word speedometer in it. They all probably have gauges and dials and things like that. I see something that looks like a steering wheel. Oh, right, there you go. See, we got adjacency items here. And that is very difficult to achieve with just tagged searches or metadata searches. You need the ability to assign so a thesaurus or similarity words that are nearby, so that way you can come up with a better improved list of search results, which is a lot more of a human. We get a better overall outcomes, more of a human interface, which is, we're humans, we're talking about what we talk about, and we need to be able to use natural language, and the better the computer can understand us, the better the results it can return. pgVector is a vector indexing system that can run inside of Postgres directly. And it's really powerful. With pgVector, you'll have the ability to not only leverage search embeddings at a high performance. You'd be able to compare arrays of numbers to each other and calculate distances for similarity search. You can also leverage all the other Postgres SQL features and capabilities surrounding that. That's why this makes this index database for vector search that much more powerful and meaningful, rather than just using a specialized vector database, which you could totally use as well. You might get a little bit better performance depending on the scenario. It's probably a lot more likely that you already have a Postgres-like system that can leverage pgVector at your fingertips without having to launch a whole new system and orchestration of that database. They actually make it pretty straightforward and simple. This is the way it should be. I love simple and straightforward. They do a really good job here. So you can initialize the extension for vector search, create a table, and the embedding will be vector, and you can say the dimensionality. How many numbers are you going to compare? The numbers are typically floating point numbers, they can be integers as well. That doesn't really matter in this case. We can insert some vectors, right? So we've got a vector here and a vector here. A vector is just an array. It's just a series of numbers in this case. And then you can apply different, oh, whoa, look at that syntax. Isn't that fancy? There's a nice little L2 distance syntax that you got here. So you just take embedding and then your input, and then it will provide the output based on how close the items are. You should also be able to, it's ordering. Oh, it's very nice. Okay, so it's ordering by, it's giving you the best performance, or the best by order, and you're limiting by 5 here. Oh, look at these others. So it supports 3 different similarity searches or distance searches. You've got the inner product, the cosine distance, and the L1 distance, L2 distance. Oh, there's 4. Okay. L2, L1, cosine, and inner product. Oh, wait, hold on. Just kidding. L1 distance says it's unreleased. This might just be documentation outdated, or that you just can't use this this operator yet. The good news is you don't have to worry about it too much, because these top 3 are more than enough than you would ever need. So essentially you have your items, and they all have an embedding, which is going to be a vector array. You have all these arrays in your database, a ton of arrays, and you want to be able to find the closest matching by another item. So you have your embedding, which is your vector, and then you can get an order of similarity by how near they are in that distance. And it really is, it's really that simple. And behind the scenes, Postgres and the pgVector indexing system just is able to bucketize all of these items, especially when you get to large numbers like millions of items or billions of items. It can better sort out all these items, so that way when you do run a vector search, you're going to be able to only have to scan so much, right? You don't want to scan the entire database. That would be, you wouldn't need a vector database. In that case, you could just scan over all the vectors directly and compare them and then sort by distance. But you need to do less work, and so by indexing, you can specifically target, and these subsets allow you to provide just a better query response time, right? Oh, you can aggregate it? Why would you? This is interesting. What are the use cases for that? We'll have to come back to that. Why you'd want to average out your embeddings. I don't know what the point, you can do it. It's great that you can do that. Why though? Oh, this is important. Indexing here. By default, Vector performs an exact nearest neighbor search, which provides perfect recall. There's a problem though. That means it's a full table scan, right? So you need to add approximate nearest neighbor search, trade some recall for speed. And so you need to apply which indexing system you want. And these are hash-based bucketing systems that you want to use. Let's create our own embeddings. We're going to do this in the easiest possible way, so we have the fewest possible steps, while also obtaining the most benefit in a real world use case. Let's take a look here. We have the whole idea behind embeddings are to capture an input, any arbitrary input, right? It could be text, photos, images, videos, audio. In this case, we're going to do text because it's pretty straightforward. And what it does is it captures the meaning in a many-dimensional space, up to thousands of dimensions. Yes, that's a lot of dimensions. It essentially takes, in order to do this, it will tokenize every word for things that it understands. For things it doesn't know, it'll tokenize in smaller chunks, maybe multiple letters or single letters, and then it will take that token array and throw it into embedding, a semantic meaning that will be able to assign all of those tokens in a way to these thousands of dimensions. And the output on the other side is going to be an array of floating point numbers, essentially a vector. The use case that we're looking at is a simple, we want to be able to search for an icon based on common human language, right? I want to use any word that's close to what I'm looking for, and I want the search engine, the computer, to find the best possible results. To start off, we are going to create our embedding string. This is going to be the string that we're going to be passing into the embedding layer. That is a very simple string. This obviously we're looking at a JavaScript function here, icon embedding string. The string is simply this right here on the screen. Icon, the icon name, categories, an array of the categories, tags, an array of tags. Very straightforward. And it's going to be one giant string, a simple string literal here in this case. Of course, we could go into a little bit more advanced embedding model by doing this ourselves locally using Python and a local. However, we can just use OpenAI's embedding model to send this string of characters straight over to OpenAI's API, and they will return to us an array with all the embeddings, with all the semantic meaning baked into a single vector. Here's why search by embedding with similarity search is just so much better. Let's take a quick peek here. For example, in a full text search scenario, we're actually going to take a look at the actual word that's being passed in, and we might pre-process it a little bit to find, other words that might match it. However, the problem is when we look at things like we want to say, I want to search for the words dog, it might miss things like canine, puppy, and wolf, which seem kind of, they're nearby, though a full text search engine will very often miss some of these scenarios. This is why a similarity search using embeddings is significantly improved. If you've ever heard about cosine similarity, well, guess what? It's actually pretty simple. It's a very straightforward and simple algorithm. In this case, cosine similarity is the only part that makes it cosine is the normative capabilities of cosine that translates any number of a distance between two vectors into, so for example, we can take a look at the terminal output here. So we've got our cosine function, and essentially it's normative because it's going to always input any input data that you provide it is going to compress it into a range between -1 and +1. So as you see, as we change these values, we see the numbers constantly changing between that range. And so you can use that normative capability to then capture the distance output between 2 points and then sort order in a way that provides the closest similarity between two vectors. So we simply take two vectors, x and y, which are just arrays. They're just floating point arrays of the same dimensions, right? So we might have an array of 3 elements, another array of 3 elements. We're going to look at them and we're going to calculate the distance. How far apart are we? How big are the numbers different? Really, it's that simple. How different are they? And the distance might be grand. And so you apply cosine onto it. And then this applying a minus on it isn't necessary. It's not a mandatory step, basically. It's just something that you can do. Potentially reduces needing to invert a sort at later in the distance. With Postgres and pgVector, right? pgVector, you can easily do this function here, which is pre-written for us, which is super great, and then just simply pass in your embedding and the embedding parameter, the row, right, the column. And in this case, the column embedding is already pre-populated, right? So we already have a giant database. We've already vectorized all of our icons, right? The names, the descriptions, the categories, all that's been vectored and stored into Postgres directly and then indexed with pgVector. Then we take the human request, like I'm searching for XYZ, and then we compare the human's embedding with the database array of all the different items in the database. And then we have a similarity. And then we also order by similarity. Notice that we've got this star here, so we've got a comma star, so we're going to capture everything from the database and all the data in the row. The default ordering already is ascending, so you don't need to specify this specifically because our cosine distance did it. I believe it's this part right here makes it a little bit easy. So we get our cosine distance. So we ascend. We don't need to worry about this part. Then we limit by 50 because, you know, after a certain number, you don't really want the human to have to start looking through a whole bunch of potentially non-related items. Now, they were telegraphing a little bit up here in in Bryant's newsletter here for Bryant's blog here. We see that they were telegraphing that there's a more complex approach to the algorithm that allows us to capture user input. When users click on the icon from what they are searching for to capture the icon, we can use that as a ranking system from a human perspective. We can capture that ranking and then apply that into the search as a weighted parameter, which allows, as people search more and they click on they make their choice on the icon they were actually looking for, we can apply that search ranking data into our embedding semantic search, which improves the quality even higher because, you know, it's what humans are actually looking for. Yes, our embedding does a pretty good job in the first place, but you can get a more complex algorithm by applying in directly the choices of the humans. And I bet you didn't know. I mean, this is actually a really cool idea. Very powerful in the industry. Users, you're actually voting. You're actually counting. You're actually giving a thumbs up, right? You're providing direct feedback. When you click on something, you've essentially upvoted that whatever you clicked on, and that data can be captured and then used to help improve overall user experience in the future. And this is exactly how they do it. This is a good way. Now, there is describing about weighting on a 50-50 basis. You don't have to weight that level, right? So instead of having splitting the weight between the cosine similarity and the user's overall count, we don't have to worry about that. We could maybe make it less than half, right? We maybe want to put more weight on the cosine similarity or more weight on the user's votings. And you probably will be able to switch that over time, right? So maybe at the very beginning, you have 100% of the weight will go on to just the algorithm itself with the embedding. And then as you collect user votes, essentially user clicks, you can slowly increment the overall clicks. A couple quick things to note before we end up here in the video. The embedding model for this example was using the text embedding 3 small from OpenAI. Guess what? You can use any other text embedding. There's a lot of things that you can run yourself, and it's probably a lot better to choose something that you can run yourself locally because it's, you know, you're paying for your own compute and electricity rather than having to pay a vendor an API fee, which also works fine. For the case on this, you want a really fast user experience. So you want the search itself and the embedding for capturing the embedding data to be as close to each other as possible. Obviously, you don't want to have to, any vendor that has a centralized service that's not like a CDN type system that has data centers distributed globally are going to reduce the performance of your search. So by bringing it closer to your end users, you're going to have a better performance search. So if you do have the ability to work with a vendor that does provide global distribution where users connect to the closest data center and their workload is processed essentially potentially just a few miles away rather than thousands of miles away, they're going to get a significantly better performance and user experience. Also, just to note that the embeddings that they've done is, you know, a string, which is just a string of letters. letters. There are other approaches that you can use, would embed maybe a little bit better for this use case, that's a more tuned specifically for this kind of search, rather than a generic overall embedding that just uses similarity search based on sentences. Depending on your scenario and what kind of search that you're expecting from your end users, you could improve the embedding process overall.